So a geometric sequence is when we're multiplying each time by something. And we call the thing that we're multiplying by the common ratio. So in our arithmetic sequences, we had a common difference, d, that we added each time. Now we have a common ratio, r, that we're multiplying each time. Sometimes you're going to be able to see r because you're good at mental math. Like if I gave you 4, 12, 36, 108, could you see that you're multiplying by 3? And sometimes the numbers won't be nice. Here, I'll give you 3 numbers where the numbers aren't nice. Seems not so bad. Oh, let's see. All right. Uh-oh. Anybody know what I multiplied by? No. The numbers aren't nice. So if the numbers aren't nice, you can always find the common ratio by dividing. If I multiplied 5 times something to get 6.1, I could go to my calculator and do, well, 6.1 divided by 5 is 1.22. Maybe I multiplied by 1.22. And then if you check this divided by this, it comes out to 1.22 again. So we can check by dividing those two and get 3. We can divide the next two, still get 3. Divide the last two, still get 3. If you get the same common ratio, and that's why they use common, because it's the same ratio no matter which 2 consecutive ones you divide, then you know you have a geometric sequence. All right. Some more highlighting. If we have those dots, that means it's going on forever. If a sequence ends, we call it a finite. Infinite if it keeps on going, finite if it stops. I don't think you have that graph in your notes, but sometimes in a geometric sequence, your numbers just keep getting bigger and bigger and bigger. And we would call that sequence a divergent sequence. But sometimes in geometric sequences, another one, the numbers that you get smaller and smaller and smaller and get closer and closer to 0. Then we call that sequence a convergent sequence. So sometimes when we're multiplying, things get bigger and bigger and bigger, and sometimes they get smaller and smaller and smaller.
What if you have a sequence that starts off like, say, like negative 1, and keeps by base, it keeps going up.
It keeps going up, but we would still say, yes, so it's increasing, but it keeps getting closer to 0. That would be convergent as well. So it doesn't have to be decreasing to be convergent. What Tristan was saying there is sometimes if you started with a negative number and kept cutting in half, it would do the same thing from the bottom side. But we'll find in geometric sequences, whenever you multiply by a fraction less than 1, then you will get closer and closer to 0. Because multiplying by a fraction less than 1 is like dividing by something. And dividing by a bigger number than 1, and you keep cutting something smaller and smaller pieces, you will eventually get close to 0. So just like our arithmetic sequences, we are going to have formulas that we're going to discover. These formulas are on our formula sheets as well. So, determine the 10th term in a geometric sequence. First of all, is this one where you can tell what you're multiplying by? Is the mental math very hard? No. What do you get?
-3.
-3. So we're going to multiply by -3. And sure enough, to jump to the next one, multiply by -3 again, and multiply by -3. So we would say our common ratio is -3. If you wanted to find the 10th sequence, you could keep going with that and keep thinking of that idea. Okay? Same thing with arithmetic. Sometimes this is time consuming though. Multiply by -3, then multiply by -3 again, and then -3 again, until you get to the 10th one. If we look at a pattern, we'll notice just the same as before. Okay, so term 1 is equal to 2. Term 2 was term 1 times by a -3. So I could even write, I'll write 2 there, 2 in brackets. And then term 3, we would multiply by -3 again. Can you see that if you multiplied by -3 again, it's like multiplying by -3 squared. And then term 4 would be 2, and you would have to multiply by -3 again, which would be -3 cubed. So if we're looking for a pattern here, what do you think, ... would happen if we wanted to find term 10? You would have to take 2, and how many -3's would multiply by to get to the 10th one? 9. And this is something we could type into our calculator all at once. So bracket -3 to the power of 9 times by 2 . And we get -39,366. Do these numbers seem like they're getting bigger and bigger and bigger and bigger? Well, the numbers are getting bigger, but they're also flipping from positive to negative to positive to negative. Does this seem like it's getting closer to a number and being convergent, or getting farther and farther and different every time and being divergent? Yeah, this one is divergent. So circle questions 3, 4, 5, and 6, and take 5 minutes to try a couple.